Hello, welcome to another video. So what we're going to do in this video is we're going to do graphing examples. So one way to learn Physics 1 or learn the definitions of things is to look at it from a different perspective and to learn how to graph this sort of things. And that way you can see the relationship between position, velocity, and acceleration better from a different standpoint. So what I'm going to do Um, wait, is I'm going to create a plot, okay, with plus x plus y. And on the x-axis over here, we're going to have time, and it's going to be in seconds. And on the y-axis, we're going to have position. This is going to be in meters, okay? And it'll go 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7 seconds, okay? And so for the first example, we're going to do, so this is an object not moving, okay? So if an object's not moving, and it's not moving for all time, what this would look like is we will see no up and down movement because that represents position, right? So if it were changing from 1 to 5, we would have it go up as a line, and then over the elapsed time it would take to do that. But for us, we're not moving at all. So for all time, we're remaining at 0 position, which is where we're at. We're just going to do it like that, okay? So for second 1, it's at 0 position. Second 2, we're at 0 position, okay, right? 0 right there. Second 3, 4, 5, 6, 7, we're at 0 position. What we want to do is we want to plot, plot the associated velocity versus time graph, okay? So let's go ahead, let's get out, oh, I even have arrows, okay, cool, I'll use this one. So let's get this guy out and we want to plot velocity versus time, okay? And it wants to be based on that object not moving, okay? 1, 2, 3, 4, 5, 6. 3, 4, 5, 6, 7. Okay. And we want to basically plot the velocity versus time graph from the position versus time. So how are we going to do that? Well, if you remember, the definition of velocity is the change in position over change in time. So from second 1, from 0 to 1, okay? So let's do it just from 0 to 1 second. The elapsed time is 1 minus 0. And the change in position is 0. We're not changing at all. So it'd be 0. So we've got 0, so this is our velocity, divided by 1 is 0. So our velocity for the first thing is 0, okay? Now, you'll notice, because our position isn't changing for the rest of it, we can similarly do the math from second to second. So v equals 0 over 2 minus 1 is 0 over 1, right? 0 over 3 minus 2 for the different seconds, that's 0 over 1. These are all going to be 0. So our velocity actually for that time will be 0, okay? And so from what this shows us is from a position versus time graph, you can get the velocity versus time graph. Okay. But because position's not changing, and the change in position over changes time and how we get velocity, we just end up with a graph of 0. But let's go ahead, let's do a different example. Let's do let's do example 2. Okay. Wait. Okay. And we want to plot, here's our plot. It looks like, whoops. We have our position versus time graph. Again, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And what we want to do is, this is our plot. We have just a straight line. Okay. It goes through all of that. Okay. Ignore my terrible this. Okay, so here's the plot that we want to do. If we want to plot our associated velocity versus time graph. So let's go ahead, let's get this going. Let's do our shapes. I wish it would scroll. Okay, thank you. All right. So let's establish our 5 seconds. And let's look at this. In second 1, okay, in second 1, we've gone 1 meter. Okay, so the change in position over change in time, which is our velocity, is going to be 1 second on the bottom and 1 on top, which will be 1. So we would go across and we would write this. Okay, just a flat line. We can do it again for velocity. So this is at 0 to 1 second. So this is going to be 1 to 2 seconds for the next one. We go up another 1, right? You look at this. Up another 1, and then over another 1. So our rise over run, right, which is our change in position over change in time, will be another 1 over 1, which is 1. And this will continue, right? Because the next one we go up 1, over 1, up 1, over 1, up 1, over 1. And so our velocity versus time graph looks like this. And so you must be seeing from this, the slope of this line is 1, right? And this is what we get for our velocity. So velocity is the slope of the position versus time graph. Okay? And that's not coincidence. Velocity is the change in position over change in time. This is the slope. okay, because it's rise over run, okay, which is literally the definition of a slope, right? You can also use this relationship to find acceleration from velocity, okay? Because acceleration is the change in velocity over the change in time. So acceleration is the slope of the position versus time. So let's go ahead, let's just do a crazy one. I'm going to give you, knowing this, wait, why does it always do that? Okay. I hate how it does this. Why? Why? I'm just wanting it to be normal. Okay. Cool. Let's move. Really? You're just not going to allow me to move that? Okay, whatever. Alright, so let's do velocity. Oh yeah, another reason you know it's the slope is check it out. Position is meters, and then we're seeing it per second. So on top of this, right, meter per second, that's the unit of velocity. Acceleration you'll see is units meters per second squared, which is meters per second over second. Okay, so that's another way it shows you that that relationship is true. That each term is the slope of the other one. Velocity, the slope of position. Acceleration, the slope of acceleration, the slope of velocity. So let's go ahead and let's just, I don't know, I'm going to come up with some random thing here. Okay, so here's some object over some time, and it's changing position. And we want to plot acceleration. Okay. One, so 0, 1, 2, 3, 4, 5, 6, 7. Okay. So let's get our thing going. We need 7 seconds on the clock here. 2, 3, 4, 5, 6, 7. That's our time. This is going to be our Excel. 1, 2. Okay. So in the first one, we're going up 1 over 1. So that means our slope for that is just a line. Okay. The next one, we have a slope of 0. It's a horizontal line. And I'll talk about this break in a second. The next one, it's up 1 again. And then from 3 to 4, it's another horizontal, so it's flat. Here, 4 to 5, it's -1. And I didn't plot that, so I need to put that down here. And then 0. And then another negative. Now you must be wondering why the breaks. Some people put dotted lines here. That's because whenever you're creating a graph like this and there's these breaks right here, you see that? How it's not, it's rigid. Whenever there's these breaks, it creates a slope that's not continuous, so it creates a non-continuous slope. Okay, and so we get a step function, is what it's called. Which is what this is. These are called step functions. Okay, and it's because they look like steps. They're non-continuous lines, so you don't actually connect these. Okay, technically. I don't want to get too specific on it, but essentially that's how it would work. So you must be wondering, well, if I want a continuous line, then you would need a smooth, right? You would need a smooth function like this. And this is how we get, what's known as calculus, where to get the slope of this line here, you have to continuously zoom in to get what this slope is, right? And that's what calculus is for, is to get the slope of, in some form, to get the slope of this line at a very small time interval, okay? And so that's why we use stuff like calculus. But we get stuff like this because in physics 1 we just have, long periods of times, not, instants in times, instant in time. And so, yeah, so we'll see like step functions and stuff like that. But yeah, that's how you do these types of problems, okay? There is one more that I want to talk about, and that's if you can get, so if you have x versus t, you can get velocity, right? And if you have velocity versus time, you can get acceleration. That's true. So you're going forward. Can you get velocity from acceleration or position from velocity? And the answer is yes. You can go backwards. So let me show you how that works. So here's this is going to be a velocity. Versus time graph. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do 10 seconds. 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. And let's say our velocity the entire time is just a flat line. Okay? So this is our velocity function. And the question asks, what does the position graph look like? Well, there's a couple things we can say, or at least one thing we can say while looking at this. We know that this is a horizontal line, right? And so if it's a horizontal line and it's the slope of position, right, we know that our main line will look like this. It'll just be a diagonal line. Because a diagonal line has the slope of a horizontal one, right? Diagonal lines, slope is flat. And so we'll know it'll look like this. But what you can do is, you can get the area under the curve. To find the line for position, get area under curve, or area under the function. So here it goes up to 5 and over 10. So the area is 5, okay, and that's in meters per second, that's the unit, times 10 seconds. This will give us 50 meters of area, okay? And so when we plot our, what we know is now a line, two, 3, 4, 5, this is 10, 20, 30, 40, 50 meters. This position in meters, this time. 2, 3, 4, 5. Okay, we go up to 50 over 10 seconds. Okay, and you'll notice our slope now is rise in 50 over 10, those cancel, it's 5, which is what this was. Okay, so going backwards, so 50, here's our area right here. And so you just create a dot at 50 over the same time interval, and then you just connect the line, and here's our slope. And so that's how you go backwards. But it is more difficult to go backwards than forwards. The other way to do it is to just try out, kind of brute force it and try out different things and see if you get it. One last thing I want to talk about harkens back to what I said about acceleration. So I said before, accel is constant, okay? And the reason I did that is because you've just seen, right, if position looks like this, velocity will look like this. So position will be a diagonal line. I need to take that off. Diagonal line. So velocity will be horizontal. And then if this is horizontal, accel, in this case, would be 0. Okay? Because the slope of this line is 0. But if accel had a value, so let's say accel looked like, I don't know, even just 1, and it looked like this, so this is our accel, then velocity would have a slope that looked like this, because that's the slope of this line, right? And then position would look like this. So this is y equals x for the line, right? This is y equals just a value. It's the slope. And this is y equals x squared. So see, this is an understood x1. It goes up to x squared. If acceleration is just a constant value like this. Okay, so if position will be a parabola, okay? And we'll see this when we work with kinematics, okay, which is our first thing. Which means that our position moves faster and faster each time. For every passing second, we change our position more and more, right? So if we're plotting position right here, our position is changing more and more, even though time stops changing as much, okay? So here's 1 second interval, right? 1, 2, 3, 4, 5, 6. Between 5 and 6, we're changing our position a lot, versus 4 and 5, we're changing a less, 3 and 4 less, right? So that's what a parabola means. Now, that's with just the constant acceleration. If you have a line, a changing accel, if this looks like this, right? If your acceleration is a diagonal line, then your velocity will be a parabola, and then your position will be, the next step up, which is x cubed, x squared, and just x. And so it really makes it more complicated if acceleration isn't constant. And that's one reason we don't do it. Okay? That's one reason why acceleration just remains constant for the course. So anyway, the main thing, I just wanted to mention that in case you were curious. The main thing you need to get from this lecture, so main thing, is that velocity is slope of position versus time, and accel is slope of velocity versus time. Okay, and then how to graph that and how to get the graph, one graph from another. Okay, so thank you for watching, and I'll see you in the next one.